Well, thank you very much for visiting with me this afternoon. Brad Calder has asked me to talk to you this afternoon about soil acidification, and I've titled my talk, Lessons Learned from Croplands of Semiarid Montana. And by lessons, I'm referring not only to experiences that I've gained in Montana, but also messages I like to deliver to growers on this topic. Hopefully some of the things I'll be talking about this afternoon are relevant to Alberta. Um, the other point I'll make too before we proceed is that my email address, if you have any questions, is rengel@montana.edu. And unfortunately, I forgot to provide that email address on the handout that was provided to you. Well, a little background about Montana. First of all, historically, soil acidity or low pH was never a concern, as neutral to alkaline soil pHs are pretty common in our state. But back in 2011, 2012, farmers in Choteau County, or at least some farmers in that county, started experiencing problems related to stands and production of cereal grains. Now, Choteau County is in the north central part of our state, and it's about 250 kilometers from Lethbridge, at least from the center of the county. And it is actually our #1 grain producing county in the state. Well, shortly thereafter, Extension MSU personnel became involved around the 2014-2015 timeline, and they started looking at the situation. A number of factors were considered and eliminated as causal effects, disease, insects, plant nutrient deficiencies, and ultimately what they found was that soil tests revealed that these affected sites at pHs less than 4.5, elevated extractable aluminum levels, and plant roots with aluminum toxicity symptoms. And that picture I showed you in the opening slide was actually a picture from one of our field sites in Choteau County. It's actually a field of barley. Anyways, this was kind of a watershed moment. The appearance of soil acidity problems in the state, we never thought we'd see it coming, but perhaps we should have. Well, my first lesson today then is trying to explain why soil acidity problems have developed in Montana. So I have to begin with textbook stuff. And if you were to turn to a soil fertility textbook and go to the chapter on soil acidity, in this case go to page 45, you'll see the following statement. Increasing soil acidity and crop production systems is caused by use of commercial fertilizers, especially ammonium sources that produce hydrogen ions during nitrification. Well, the second part of our lesson has us looking at fertilizer and nitrogen use history in Montana. And this is what I've done here. I've basically made a plot of the tons of nitrogen sold versus time. And when you do so, what you'll see is that we've had a tremendous growth in fertilizer nitrogen use since the mid-1980s. Right now, we're presently, in terms of fertilizer nitrogen use, we're up about 3x what we were at the levels in 1985. Urea dominates the nitrogen sources that we apply. It's about 86% of the N applied, and urea is an ammonia-based product. So if we combine the two effects, that we know that ammonia-based products result in development of acidity, and our consumption is going way up, it's only natural to think then that acidification is occurring in our state. And then the other factor, which is maybe compounding things a bit, is the fact that beginning in the early to mid-1990s, direct seeders started becoming very popular, and we underwent what I call this tillage reduction revolution. And now most of our landscapes or our fields are managed as no-till, and surface applications of nitrogen are very common. Well, the second lesson I'd like to visit with you about came from surveys I conducted of farms in Choteau County. And one of the things I was struck by was the issue of field variances and the fact that spatial differences in soil pH could be quite large over short distances. Why this is important is because aluminum availability in the soil is closely tied to soil pH. And one of the big problems with soil acidic conditions is appearance of aluminum toxicity. And I have an example of that in this slide here. In the center of this patch, the pH is about 3.8, and growth of this winter wheat crop is severely affected by aluminum toxicity. You go just a few feet to the outside where growth appears to be normal, pH is 5.1. So one of the things that is apparent in our surveys is that problems with acidity are often very patchy in the field. And this has implications too for soil sampling. It means that when we're trying to identify problems in the field, it's important to keep our sampling localized and to collect samples from both good and bad areas in a paired fashion, preferably. This is another example of aluminum toxicity in the field, and it's a follow-up to my previous slide. And the point I'm trying to make here with this slide is that what we have found in many cases in our surveys is that the lowest pH is often found in our low-lying areas in the field, or in what I call foot slope positions. And as you move up the slope in a field with some topography, pH tends to increase. Anyways, it can add to the patchiness in the field. It's not always the case that the lowest pH is in the lowest slope position, but in many cases I found that to be true. This is an aerial view of a safflower field near Big Sandy, Montana. It's about 80 kilometers south of the border, and it was taken with a drone. I provided this picture here because I wanted to illustrate the patchiness effect that you often see with aluminum toxicity symptoms. In this case, the field is very flat, has little or no topographic features to it, but still there's this patchiness effect going on. And again, this is, to me, tied a lot to the sensitivity that aluminum availability has to soil pH. And I'll explain a little bit more about that in a moment. Okay, these are some close-up views of the plant roots from that field that I just showed you. In this case, the areas which were affected by aluminum toxicity. One of the ways to recognize aluminum toxicity is by inspecting the roots. Often you'll get this necrotic root tissue, almost looks like a plant disease. You can see where it could be confused with a plant disease or root disease. You get stubby roots, and in this case with the safflower, you sometimes see this J-shaped effect. As I mentioned previously, small differences in soil pH can have a big impact on aluminum availability. And all soils, at least all mineral soils, have a lot of aluminum in them. But what's interesting is that the available aluminum, or the extractable aluminum, changes markedly with soil pH. And you get what is referred to as this exponential increase in aluminum availability as soil pH starts to flow 5.2. Now this is data I collected from a farm location in Choteau County, one farm location, but it's very typical of all mineral soils and would be typical soils in Alberta also. It's what I call kind of a textbook relationship between extractable aluminum and soil pH. What happens is as pH starts to fall below 5, the solubility of aluminum minerals in the soil increase. And with that comes more opportunities for aluminum toxicity. Anyways, these small differences in soil pH then can have a big impact on available aluminum, and it helps to me to explain some of the patchiness and abrupt boundaries you sometimes see between good and bad growing areas in the field. Third lesson I'd like to visit with you about is this phenomena of soil pH stratification with depth that is very common in no-till situations. And we found that in our 5-farm survey in Choteau County. In this case, I collected cores from areas of the field where aluminum toxicity symptoms were evident. And I've plotted here the soil pH with soil depth. And you can see that the most acidic situations, or lowest pHs, are found in the shallowest depths. And this is because our fertilizer is applied near the surface. You'll notice that we go down just a little ways into the soil profile, maybe 4 to 6 inches, pH is a little higher. By the time we get down into, say, 12 to 15 inches, we're starting to get to neutral to alkaline pHs. And the reason for this is because a lot of our subsoils have natural calcium carbonates in them. And I suspect a similar situation then exists in Alberta. Direct seeding probably has contributed a little bit to the stratification effect, though I don't want to blame everything on no-till and direct seeding. But you'll notice that the pH is lower, say in the 0 to 3 or 0 to 2 inch depth layer than it is in the 3 to 6 or 2 to 4 inch depth layer. And if we had some tillage going on, I would expect there to be not as great a difference between those two depth layers. For comparison's sake, I'm just showing the soil pH profile from Washington State. And it's a similar situation to Montana with one slight difference. And that is in Washington State, their lowest pHs are found just below the soil surface. Right at the soil surface, pH is not quite as acidic as it is, say, at a 2 to 4, 2 or 2 to 3, or 2 to 4 inches down in profile. And the reason for that is in Washington State, the fertilizer is most frequently injected into the soil with knives. And so nitrification occurs right in this area versus near the surface like it does in Montana. Just anyway, similar picture, but just slight differences at the soil surface, and emphasizing the fact that in no-till, most of the acidification happens near the depth of fertilizer placement. Well, the fourth lesson I'd like to visit with you about is results from some of our on-farm lime strip trials. And I've got some little bit of data and some photographs I'd like to share with you. Liming is obviously a long-term solution to remediating soil acidity. In Montana, and as in other parts of the northern Great Plains, proximity to lime material and application costs are really big challenges. In Choteau County, a lot of growers are experimenting with sugar beet lime, so we use that product in some of our sugar beet lime trials, and we conducted them at 3 farm sites. Well, the first part of my discussion here I'd like to focus on is the lime required to correct the soil acidity. And what I have plotted here is the soil pH change from 2017, when we applied our sugar beet lime, versus the lime application rates. This is a summary from 2 locations. The pH, initial pH, in the upper 4 inches of the soil was 4.6 at Fort Benton and 4.8 at North Geraldine. Both soils are a Bearpaw clay, Vida clay loam. And so if our target pH is 6, what we're looking at is having to raise the pH about 1.3 pH units. And that equates to about 2.5 tons of sugar beet lime. And you start doing the math and everything, what it comes out to is about 1.4 tons of calcium carbonate equivalent per acre for that change, or 1 ton of calcium carbonate for every pH unit. You start doing the math on all these numbers, and what you find is that the cost of the lime inputs may exceed $400 per hectare or $165 per acre. This is for sugar beet lime, which is where the product is free and all you're doing is paying for the transportation costs. So one of the challenges I think that I've had is trying to convince growers that a lot of cost inputs are required to correct this acidity problem. This doesn't make people too happy, obviously, to hear this. The reason why I mention that is because a lot of growers have pondered the idea of using seed-placed lime, pelleted lime applications to correct problems and to kind of defer the production costs. And the point I'm trying to make is they likely will not correct the soil acidity problems, given the lime requirements needed to correct this problem. Well, that was the bad news portion of this lesson, but there's actually some good news with this lesson, and that is looking at the longevity of a liming application. And there was an excellent study done by Malley and his associates back in the mid-1990s on this topic. This was work that was done in Alberta and Saskatchewan. And I just want to read to you some of the conclusions of the study. What they found was that a single application of lime maintained or increased soil pH and crop yield for 16 to 27 years, and that the economic value of that increased yield from lime was substantial at all sites, and that because of this long-lasting effect, the cost of applying lime to an acid soil should not be considered a normal production cost, but rather a capital investment amortized over a long period of time. And this has been my message to growers in Montana. We do have some long-term cropping system studies we can draw on. And in general, we have found that our long-term cropping system studies, where we have looked at cumulative nitrogen inputs, reveal really information that is consistent with this article by Malley. One of the issues that's come up in our meetings with growers is the need for lime incorporation. And our research shows that lime incorporation with tillage is necessary to affect the soil pH in the surface layers. Question then becomes back from no-till growers, well, if we do this one tillage event to incorporate the lime, do we affect soil organic carbon? Because there's some thought, at least some of the growers, that we're going to affect soil organic carbon. So we looked at that at two of our locations, at Fort Benton and Geraldine, and I've summarized some of the results here. These are, by the way, we did this very carefully. We looked at 18 georeference locations at Fort Benton and 24 at Geraldine, both in 2017, before and after the tillage event that was incorporating the lime. And you can see there's really no negative effect of tillage on soil organic carbon at either location. So what we conclude is that a single tillage event does not destroy soil organic carbon. And this is consistent with long-term studies in Wyoming, and also is a very good study in Saskatchewan by Bond and others. And I'll just quickly reference that article here. The title was Effects of a Single Cycle of Tillage on Long-Term No-Till Prairie Soils. The conclusion was that overall imposition of one cycle of tillage on long-term no-till soils appears to have little effect on soil properties or crop growth. And one of the soil properties they did look at in this study was soil organic carbon. Well, I thought I'd share with you some photographs of our sugar beet lime strip trials. This happens to be our location near Fort Benton, Montana. This is a photograph in the end of May 2018. It's a field of lentils. The lentils we found are very susceptible to soil acidity, and you can see our limed areas here that are very much more greener than the more chaotic unlimed areas. Obviously, rhizobia growth and nodulation are being affected. Here's another check strip over here without a lime. This was taken about 7 months after the lime application. This is our sugar beet lime trial near Geraldine. The photograph was taken in 2019. And again, you can see growth differences between our limed area and unlimed area, appearing very early in the season here. This is that same field site a few weeks later, the end of June. You can see differences again in growth between the limed and the unlimed area, and the nitrogen content of the peas here, the yellow peas, is quite a bit higher than the unlimed area. I mentioned nodulation. These are some roots we dug up from that field site that I just showed you in the previous slide. These are limed areas. You can see nodules in our plant roots. And then if you go to the unlimed area where the pH is about 5.1, there's really no nodules developing. So this has been a consistent theme then at our sugar beet lime strip trial locations. Finally, just the yield that we got. There was a good yield response at this location in 2019. There was about a 7 bushel yield increase with the lime application. Well, in addition to some of the pulses, durum is also very susceptible to low pH. And this is a drone shot from 2020, and it's at the same location as our yellow pea slide. It's basically our sugar beet lime strip trial at North Geraldine. And if you look at the drone shot, I've outlined here where our strips, our different lime application rates are located. This is our check, are 4 ton, 0, 4 ton, 4 ton, 0, and then a 2 ton rate of sugar beet lime. And you can kind of pick out, or you should be able to pick out, the plus and the minus lime strips in this aerial drone shot. But the thing to point out, though, is that the effects are not really continuous across the entire field. It's not always possible to see the differences at every location, paired location. And this speaks to the patchiness of soil acidity in the field. We did measure yield in 2019 at this location via the combine yields, and there was about an 8 bushel response to the lime application, at least the average of the 2 and the 4 ton rate versus the unlimed area. Another slide here, a close-up now of the durum roots from some of the check areas where we didn't add lime, showing aluminum toxicity symptoms. I mentioned clubbing of roots. This is really evident in durum. You get necrotic tissue, clubbing of the roots. One of the symptoms then of aluminum toxicity. Okay, well, the final thing I'd like to talk with, or the final lesson, deals with some work we did with seed-place phosphorus and its impact on cereal grains at a field site with a very acidic soil pH. And the impetus for this work was based on some studies that were done in Oklahoma, some dating back to the early 1990s, which showed a real benefit to phosphorus fertilizer placed with the seed at field sites with very acidic soil pHs. And this work was done, again, in the early 90s, some of it, and it was all done with winter wheat. And so we tried to look at this impact up on the Highwood Bench, which is in Choteau County. Our test crop was durum. We conducted studies both in 2018 and 19. I'll only present the results from 2018 because in 2019 things got, everything was held out. Anyways, it was set up as a replicated small plot study, kind of a factorial, 2 ag lime rates, plus ag lime at 5 tons per acre, and minus ag lime or no lime, and then mixed with 5 P rates. The study setup looked something like this. Of course, it was replicated, plus ag lime, minus ag lime, and then our 5 P rates, 90, 60, 30, and 15 units of P2O5. And the test crop was durum because we know that was very susceptible to soil acidity. And what you can see in this picture is very big differences crop growth at this field site with the application of ag lime. The base pH is 4.4, with the ag lime it's 6.1. If you look at a close-up of the plants, which I have in this slide, this is in the unlined, or excuse me, in the area without any phosphorus and no lime. You can see that it kind of mimics phosphorus deficiency. You get the purple coloring in the lower leaves. Okay, so let's look at the response to seed-place phosphorus at this field site. And what you can see is it really seems to mitigate the aluminum toxicity problems. And again, what you have pictured here is our check, and with 90 units of P2O5. This is both these plots are unlimed areas. Okay, and you'll see some obvious differences in growth and also increases in tissue phosphorus concentrations, which are interesting because field site tests very high in P, which suggests there shouldn't be a response to a phosphorus fertilizer, but in fact there was, and suggesting that at really acidic sites, even though the soil test is high in P, a lot of that P becomes unavailable. Let's look at those same 2 plots closer to maturity. You can see, again, the differences in growth are still evident. Very big differences in canopy density near maturity. Okay, so let's move on and look at some of the yield results from this trial. And I've got that summarized here. And there was a very big difference in response to phosphorus depending on whether ag lime was applied. So let's look first where ag lime was applied. The yields are about 46 bushels per acre. But then let's go look at our unlined treatment now, right here in the blue. First of all, without phosphorus, the yield's about 23 bushels. So the soil acidity effect amounts to about a 50% yield loss. relative to ag lime or plus ag lime treatment. However, we add phosphorus fertilizer and the yield, you get this incremental increase in yield up until about 60 pounds per acre, and the yield of the unlimed area equals that of the lime. So plus phosphorus fertilizer, at least at 60 and 90 units of P2O5 equals the positive ag lime yield. That's about a 22 bushel response to phosphorus fertilizer. And of all the trials I've conducted in Montana over the last 37 years, this field site was most responsive to phosphorus that I've ever found. And it was kind of interesting in that our biggest response to a phosphorus fertilizer I ever found was at a field site that tested really high in P. Well, the conclusion from all this is that phosphorus fertilizer may provide some short-term solution or remediation, not remediation, but short-term adaptation to field sites with acidic soils. However, the thing we want to emphasize, it's not remediation, and we're not improving soil pH, but we are at least finding some way to adapt to the situation. Well, summarizing then some of the information I've talked about this afternoon from my lessons, some of the take-home messages. First of all, croplands in Montana are becoming more acidic, and we believe that fertilizer inputs are a big reason. And this is particular in light of the fact that we've seen a big growth in fertilizer use over the last few decades. Right now, again, we're 3x our nitrogen use rates since 1985. No-till may have contributed to pH stratification. I certainly don't want to blame everything on no-till and the direct seeding revolution, but I think it certainly has exacerbated the situation a bit because we aren't getting the mixing of the soil layers that we once did with tillage. Our problems in terms of acidification are not unique to Montana. Other Great Plains states and areas of Canadian provinces are being affected similarly. Aluminum availability we've seen is closely linked to soil pH, and we've found that toxicity symptoms can happen if the soil pH starts to fall below 5. Our field surveys, the soil pH in Choa County, revealed large spatial gradients in soil pH, and many of them are related to terrain and topography, though not always. And then there's certainly stratification with depth. So what this means is where you sample in a field is certainly important. Things like slope position may impact how you interpret your results of a pH survey of a field. And certainly you want to separate in your surveys sampling from areas with good growth versus poor growth areas. Sampling depth matters. That's another consideration. Typically, we take samples from the top 6 inches, but we might want to consider breaking the samples apart into a 0 to 3 and 3 to 6 inch depth layer segment because of the stratification effects that are going on. A few other comments then. Liming is required for remediation. Tons of lime per acre are required, so the cost inputs are quite high. That's kind of the downside, but the effects will likely be long-term. And the results certainly from that Malley and others did in Saskatchewan and Alberta showed this, and some of our work is showing a similar effect. We've seen that in pulses, nodulation and fixation can be affected at soil pH levels less than 6. And lentils right now appear to be very sensitive to soil pH, but the evidence here may be more anecdotal. And finally, things like management options exist to cope with this situation, things like seed-placed phosphorus. I haven't talked about cultivar selection, but certainly that's important when we start talking about acidity problems and aluminum toxicity. But ultimately, these are not options which remediate the situation. Liming is the only way to remediate. In the long term, these fields that are becoming acidic are going to have to be limed. So thank you very much. And for more information and links to additional resources on soil acidification in Montana, you can visit Dr. Jones's website at the that I have indicated in this slide.